So, welcome back friends. We have been talking about Klein-Gordon equation. Now, the Klein-Gordon equation, we are in principle talking about the problems, or I shouldn't want to call it as problems, but the issues with the Klein-Gordon equation. As we have seen that the moment you put a relativistic wave equation, you end up having two solutions for it, and both the solutions can be present. Essentially both the solutions are allowed by the equation. Now how to deal with it, and then we saw that the moment I put in first of all, the first main problem which arises is the interpretation whether the density, the probability density rho is the same, can we give it an interpretation as probability density or not. This is the thing. Okay. If you derive a probability density and a probability current in the relativistic framework, you end up having equations in this particular fashion, and the first condition what we saw was that the rho can be negative. Essentially we say that rho can be negative. Now this is a serious issue of course, but then what we said was, okay, we do not want to give it as probability density interpretation, but instead we will give it an interpretation in terms of charge and color, charge density, essentially charge density and current density. Okay. And so going ahead with it, so to interpret properly in terms of charge and current density, what we did was we coupled it with electromagnetic field. For this I wrote tell you how to write it down in terms of an electromagnetic field in the relativistic framework, and we wrote down the electromagnetic field equations by simple rules. Essentially the quantization rules are different because the momentum also has E mu in it, essentially E in times A mu, P mu is equal goes by this quantization, new quantization or a new rule, essentially by this rule, and we from this you get back your Klein-Gordon Lagrangian and the Klein-Gordon equations with the electromagnetic field, essentially. Now what we see is that moment we define it in terms of the electromagnetic field, of course the charge can be both positive and negative. If we interpret it in terms of charge density and current density, of course the electric charge can be both positive and negative, because both the solutions are allowed, because the Klein-Gordon charge Klein-Gordon field represents both positively charged particles as well as negatively charged particles, and you can always have a situation in which the electric charge density could be negative, because if there are large number of negatively charged particles in the initial state or at the moment you are considering it, at the same time you can have a situation in which there are large number of positively charged particles. So the interpretation in terms of charge density and current density makes sense. Then we went ahead and said that the Klein-Gordon field represents a spin zero field, essentially. Now there are several ways of seeing this thing, essentially either in terms of a quantum Lorentz actually looking at representations of the Lorentz group, but a simpler way of looking at it is to look at the non-relativistic reduction of the Klein-Gordon equation, essentially. Now the Klein-Gordon equation, to derive the non-relativistic equation, we started with a heuristic argument, essentially. You may call it as a heuristic argument, which we did in the last class. Okay. What we said was that I start with a test wave function, which is a non-relativistic wave function in which the mass of the momentum part or the velocity part of the particle is very small, essentially. So essentially you start with a wave function which has some normalization n0 and an exponential e power I mt, essentially m is the dominant factor essentially compared to the rest of the wave function, essentially. Okay. So t e is nothing but m essentially here, and essentially and p is a very small piece, so you express your wave function in this particular fraction. Now by definition this is a non-relativistic wave function essentially. Okay. Now okay, this is not covariant under Lorentz transformations. Of course you can always go to another frame and everything, but you can boost it and so on, so essentially, but still we to start with it is a completely a non-relativistic wave equation, wave solution. Now you put it back into the Klein-Gordon equation. Now you well knowing that it will not be satisfied essentially, because you do not have a dispersion relation which satisfies this thing. If you put it back this particular, you do not get E square equal to E square plus M square essentially. And what you actually have the assumption is that you have to put in a further assumption that the double derivative is smaller than the first derivative, or in real sense essentially what you are asking is that the energy of the or the first derivative is much smaller than the mass of the particle essentially. This is the assumption you put in, and you put it back into this and it gets simplified essentially. You get it gets significantly simplified and you end up having the Klein-Gordon the Schrodinger equation with no spin terms essentially, with no spin terms. Okay. So you get back your time dependent Schrodinger equation in this particular for free particle. Of course we had done it for free particle essentially, and this again shows that the then we claim that this again shows that the Klein-Gordon equation represents a spin 0 particle, because there is no spin terms like in Pauli term matrices or any of these things which we studied for spin in ordinary quantum mechanics. Fine, very good. Now you can ask me, you can question me, okay, you have started with something. So you can question me that is the proof which you have shown, that is it rigorous or not. The point is that is the proof is rigorous or not. In fact it can be shown rigorously by various mathematical methods essentially, that the Schrodinger equation, okay, we will not go into the details of it essentially, but this is a very standard technique. Actually this technique which I have used essentially is a very standard technique to derive the non-relativistic reduction, and it works. Now is this foolproof in the sense that yes, it can be shown by concrete mathematical arguments that in the limit the velocity of light goes to velocity of light goes to infinity essentially, or in the limit where the particle has velocities which are much smaller than the much smaller than the velocity of light. What happens is you end up having non-relativistic Schrodinger equation as the limit of the Klein-Gordon field essentially. So it can be proved mathematically and rigorously. Rigorously that the Klein-Gordon the Schrodinger equation is indeed the non-relativistic limit of the Klein-Gordon field equation. So I hope this will set essentially any doubts one has about the technique we used to derive the non-relativistic reduction. Now of course now what do we want to study. At the end of the day, what we do in quantum mechanics is that we consider we have a Schrodinger equation, we put in potentials and study whether there are bound states or scattering states and various aspects about it and everything essentially. That is what we would do. Now, so can we do everything what we can do in ordinary quantum mechanics in relativistic quantum mechanics? That is the question, that is what we have been framing it, right, essentially right from the beginning. That is what we have been trying to do. Now, now the point is that suppose if you start with a Klein-Gordon field, now you say the main difference which we have seen is that it is not a single valued solution. Okay, the Klein-Gordon field has always two solutions which are positive energy and negative energy. So it has two dispersion, it satisfies two dispersion relations. Okay, E is equal to plus square root of p square plus m square, and E is equal to minus square root of p square plus m square. Now this will propagate everywhere you go further essentially. Okay. Now for this reason it is quite different from ordinary quantum mechanics where you have only Schrodinger equation which has a single valued solution essentially. Okay. Now whereas in the relativistic quantum mechanics you have double valued solutions, you have particles and antiparticles which I have given interpretation, which will put them in a much solid footing essentially in the coming days essentially. Now this will create problems. It propagates, this multi-particle solution propagates when we try to build do things like what we try to do in ordinary quantum mechanics in relativistic quantum mechanics or quantum mechanics in the relativistic sense essentially. So this is a major issue essentially, and this will show all the pathologies associated with using ordinary relativistic quantum mechanics to solve problems. But still there are, why do we study this topic is because there are a lot of things which are useful essentially. For example, one can study bound state solutions with Klein-Gordon field, and there are some situations in nuclear physics where the Klein-Gordon field or the Dirac field is much more useful to study directly rather than using field theory language which is almost intractable in the case of in some cases essentially. So there are uses and applications of the Klein-Gordon field in nuclear physics, condensed matter physics, and similarly of the Dirac equation also in nuclear physics and condensed matter physics, and that is precisely why we are trying to study. And also it puts the study of field theory on a much stronger footing essentially. Why do we need a framework which is much more robust and solid like quantum field theory? And this motivation is put on a much solid footing, and you can have a physical intuition, you have the physical problems associated with the relativistic quantum mechanics before going to a relativistic quantum field theory. Okay. That is precisely, these are the main motivations why we are studying this topic essentially. So to continue, so should we so what we do is now that we try to ask the questions, can we do again and again that can we do the same quantum mechanics or topics which we do in quantum mechanics in relativistic quantum mechanics. The first thing we will do is ask the question, can we build wave packets. Okay. In quantum mechanics what we do, I think in quantum mechanics first couple of lectures or third lecture or something, we first thing what we do is build actually wave packets essentially. We collect a bunch of plane waves and we give a dispersion, we give a small spreading essentially along some Gaussian or something and start building wave packets essentially. Now can you do something similar here? And the answer is yes. So we can start with yes. There is nothing stopping us writing wave packets essentially. So what happens is that when you put in wave packets, so let us say that I put in a wave packet with scalar fields, scalar particles essentially, which are essentially solutions of Klein-Gordon equation essentially. So you collect a bunch of solutions of Klein-Gordon equations. So let me call them as let me collect only the positive energy solutions of the Klein-Gordon equations, collect a bunch of them, let me call them a phi plus, and I write them in their momentum representation, solutions of Kg equation which are positive energy. Okay. Now you collect a bunch of solutions and then you can write the corresponding wave packet as phi x bar of t integral d cube p by 2 pi cube e power I p bar dot x bar, and then I will introduce another function which I call it as some a p plus essentially, okay, a p plus of t, and then put these functions essentially phi plus of t of p, where this function a p scans the momentum essentially around, this is the function a p which is given by some sort of okay. So this can be some sort of a Norra-Gaussian, okay, can be thought of as a Norra-Gaussian, and then I collect it around a Norra-Gaussian around peaking at around the origin, okay, and then I can write some such function of this particular type. Now the point is that you can this is not unique, this is not the unique wave function, you can construct many kinds of wave functions essentially, but because you can always construct them by collecting a bunch of solutions of the Klein-Gordon equation essentially around certain point essentially, it's around a certain value of the momentum or so on, so essentially. Good. Now we can construct wave functions. Now what is the issue with this essentially? So suppose if you have wave functions, now so you say that okay, I can do all whatever I can do in non-relativistic quantum mechanics. In relativistic quantum mechanics the answer is not strictly correct essentially, okay, the answer is not strictly. One of the first person to construct relativistic wave packets and see the problems in the relativistic framework was essentially Schrodinger essentially. So what he observed was that this was observed in the case of Dirac theory, but I am just mentioning it in the Klein-Gordon equations also, and because we will do the same thing with the Dirac theory a bit later on after doing the Dirac theory and introducing the Pauli matrices and so on, so essentially, and the gamma matrices and everything. So but I am just mentioning it here so that we have an idea. So the point is that you take these wave functions, put them in some potential and everything and calculate the transitional amplitude and so on, so, and if the potential is very strong it will lead to problems essentially. So the problem is that you cannot, in the presence of any potential if it is strong, a wave function made up of purely positive energy solutions will not lead to physical answers essentially. So it will lead to always some problems because the presence of a potential, if it is strong enough, it will lead to creation of particles and antiparticles essentially, and the antiparticle current will appear automatically. Okay. So the antiparticle current will appear automatically, and if you put in the calculate the current, essentially the currents will be rapidly oscillating because of this feature essentially, which is called Zitter-Bitter-Wiegang. This is German. Schrödinger. This was first discovered by Schrödinger essentially in a very nice paper while studying Dirac theory essentially. Okay. So you can construct wave functions, but the wave functions will not solve any problems essentially. The basic idea, the problem is that in the presence of any potential or any interaction, you cannot separate the positive energy states and negative energy state. So even if I start with a wave function which is completely positive, made up of positive energy states, in the presence of a potential, the negative energy coupling will appear into the theory, the negative energy states will appear because of the coupling with the potential, okay, in the theory, and automatically it leads to rapid oscillations and funny behaviors and unphysical picture, okay, unphysical picture. We will see this in Dirac theory. Okay. So this is about constructing wave functions. So you see that you can construct wave functions, and then you can construct wave functions, but in the relativistic case I am just mentioned it to you, I did not show it to you that this will lead to always problems, essentially unphysical problems, which we will have a more understanding in the Dirac theory, which will come later. Now what about solving potentials? Essentially there are some potentials which you can solve exactly, okay. There are some potentials which can be solved exactly in the Klein-Gordon field essentially. Okay, there are some potentials which you can solve exactly in Klein-Gordon field, but they may not correspond, but one should always be careful that yeah, so one should always be careful that in the non-relativistic limit these potentials may not have a exact solution essentially, okay. They may not be solved exactly essentially. So we may have to use some other perturbation techniques or some other techniques essentially. So it is not always true that potentials which can be solved in the Schrödinger equation can be solved exactly in the Klein-Gordon field or vice versa essentially. So it is not always true, and the vice versa is also not true, that potentials which can be solved exactly, okay, in Klein-Gordon field are not equivalent to the potentials which can be solved in, okay, in the Schrödinger picture essentially, even if the non-relativistic limit is perfect essentially, okay. So but these potential where they study, they again as I mentioned to you, it can be it has applications in nuclear physics and condensed matter physics essentially, okay. So the point we will say is potentials many of the times some of these solutions are solved numerically also, okay. In Schrödinger wave equation need not be solved exactly in Klein-Gordon field and vice versa. So the opposite is that potentials which can be solved exactly in Klein-Gordon field need not be solved. Okay, the key point is that need not. Okay. It's not always guaranteed that they can be solved. The potentials which are solved exactly in the Klein-Gordon field can be solved in the Schrodinger wave equation essentially. Okay. So now let us look at are there any issues with solving potentials. Okay. We will start with the simplest thing. Okay. We will start with the simplest potential, one of the first potentials which we start essentially. Okay. And like in ordinary quantum mechanics, and see if there are any problems associated with it in relativistic quantum mechanics. Okay. I will stop here, and yeah, I will stop here.